All right, so we're going to be talking about graphing exponential functions. So an exponential function is a new type of function. It's sort of similar to something we learned about last semester called geometric sequences. Geometric sequences were kind of a version of this. So hopefully you remember a geometric sequence is a list of numbers. It's a sequence that follows a constant multiplication pattern. So 3, 6, 12, 24, dot, dot, dot. This is a geometric sequence. Again, remember, a geometric sequence follows constant multiplication. So in this case, we are multiplying by 2. 3 times 2 is 6, 6 times 2 is 12, and so on. And we have a starting value here. Well, our exponential functions are going to be very similar to that. So here we have kind of the general form that our exponential functions are going to take. Y equals a times b to the x. We call it an exponential function because x there, our variable x, is an exponent. Again, that's why we call it an exponential function. The two numbers that are going to be changing here are going to be this a value, which we call the starting value, or y-intercept, or another thing we sometimes will call it is the zero term. That's more related to our geometric sequence terminology, right? The zero term of our sequence, we call this term 0, term 1, term 2, term 3, and so on. And then b, that's going to be called the multiplier or growth factor. And we'll see how that works. That is more analogous to this here, right? Multiplying how we move from one term to the next of a sequence. All right, so here's our first example. We're going to be trying to create a table and a graph for this exponential function we have here. So we have a starting value of 15, 15 times 1/3, that's our multiplier, to the x power. So filling out a table, I already know that this value here is going to be 15. And I can kind of confirm that by evaluating my function. If I do 15 times 1/3 to the 0 power, again, replacing my x with a 0, I get 15. Right? So that's my 0 term, my y-intercept when we graph it, or we can also call that the starting value. And the multiplier is going to show up as how we move forward in our table, right? How can we move down in our table? We're going to multiply by 1/3. Hopefully you remember when you multiply by a fraction like that, it's the same thing as dividing by our denominator. So dividing by 3. That means the next value in this table would be a 5, because 15 divided by 3 is 5. And then 5 divided by 3 is 5/3. And again, we'll kind of confirm that here using the calculator. So if I plug in 1 for my exponent, right, plug in 1, I get 5. And then if I plug in 2, I get 1.6 repeating. If I change that to a fraction, you can see, yeah, that is this value here. And if we are dividing by 3 or multiplying by 1/3 to move up our table, we got to do the opposite of that. We got to multiply by 3 to move up, move backwards in our table, move back up. So multiplying by 3, we would get 45. And then again here, we'd get 135. Again, I can confirm that using my function here. So I'll plug in -1. And see here, I do get 45. And then I can plug in -2. And you can see here, I get 135. So a few different ways we can go about filling out this table. We can use the starting value and the multiplier. We can also evaluate it using the function there, right? Replacing the x value with these different x's. So next step, we're going to try to put this onto a graph. When we are graphing an exponential function, we want to make sure that we include at least 3 points. So I'm going to try to include these 3 points here. I'll also go ahead and put that one on there, but I'll have to be heavily approximating because that is a pretty small value. So on this graph, on the graphs that you'll receive, you'll have your x-axis scaled, but you need to determine a scaling for your y-axis to fit some of these numbers on here. So I'm going to go ahead and just count by tens. That's a nice round increment to count by, and I think I should be able to fit everything on there. So 10, 20, 30, 40, and I guess I need to go up a little bit higher to go up to 45, so we'll go up here to 50. Now, this doesn't have to be perfect. I'm just kind of going to be approximating a lot of these points, but I want to make sure that I'm counting by a nice even increment, like counting by 10, 10, 10, 10, 10. I don't want to change the scaling on there, and I want to make sure to space it out nicely. Next, I go ahead and plot these points. So I'll start here, -1, that is all the way up here at 45, right there in between 40 and 50. At 0, that's 15. Again, that corresponds to our y-intercept. That's actually part of the equation here. At 1, we should be at 5, so it'd be right there between 0 and 10. And then finally, I can kind of approximate this one. At 2, we are at 5/3. That's very, very close to 0, relatively speaking. So you can see this graph starts up high on the left and is a decreasing graph as we move to the right. So I'll try to connect these dots as best I can, kind of draw a smooth curve, and there. So exponential graphs are always going to be going up on one side, and they're going to be flattening out along the x-axis on the other. So in this case, our graph is pointing up on the left side here, and it's flattening out on the right side. We're going to see graphs that kind of flip that around. But we have included at least 3 points. We actually have 4 of them on here, and we have a nice exponential graph. All right, let's go ahead and move forward and do a couple more examples. All right, so the next one here, we have y equals 6 times 3 to the x. So 6 is our starting value, our 0 term, our y-intercept. That always goes when x is 0. So that's going to go right there. Again, we can kind of confirm that using our calculator. 6 times 3 to the 0 power, right? If I replace x with a 0, I get 6, right? And then our multiplier is how we're going to be moving forward in our table, so from 0 to 1. So we're going to be multiplying by 3. So that means that this next number here would be 18, and then multiplying by 3 again, it would be 54. If we are multiplying by 3 to move down our table, to go the other direction would be dividing by 3. Right? So 6 divided by 3 is 2. 2 divided by 3 would be 2/3. And again, I'm going to go ahead and quickly confirm all these values here using the calculator. So I'll replace x first with -2. Right here, -2, we get this value, 0.6 repeating. If I press my fraction button there, you can see, yes, that is 2/3. I'll go ahead and replace with a -1. Yep, we get 2. And then we'll replace that with 1. Yep, right here, 1. You can see we get 18. And finally, replace it with a 2. Yep, we got 54. So you can kind of fill these tables out in a couple different ways. You can use the starting value and multiplier approach, like I started with, or you can evaluate them using a calculator of some sort. All right, now I want to go ahead and take this and put it on the graph. So in this case, I'm going to go ahead and count by 6s, just sort of choosing that. You can pick really any sort of scaling as long as you're going to fit enough of your points on there. You don't want to count by like 1s. That would be making a ton of little marks to try to get up to even like 18. But I'm going to count by 6. So 6, 12, 18. Next one here would be 24, I guess. So now I'm going to go ahead and plot these points. So we'll just go here. -1 is at 2. 2 would be a little bit here. So 2, 4, 6. Yeah, so about right there. 0, 6. That is our y-intercept, starting value there. 1, 18. That would be right up there. And then 2, 54. That's way off the screen somewhere up here. So I'm not going to go ahead and plot that one. I will go ahead and estimate this one, though. -2, 2/3, that's going to be very, very close to 0. So hopefully you can recognize this is similar to our last graph, though it's been flipped a little. Instead of being up high on the left side and flattening out along the x-axis on the right, if we go back and kind of see what that looked like again, remember it was up high on the left and then flattening out on the right, our graph's kind of flipped from that. It's flattening out along the x-axis over here and going up on the right side. So let me go ahead and just kind of sketch this curve in. It doesn't have to be perfect. And I'll go ahead and put arrows on the end to indicate that it is continuing. So this graph is an increasing graph, and that's dictated by our b value. Anytime our b value is greater than 1, we have an increasing graph. We call that growth, exponential growth. A lot of things can be modeled using exponential growth. And then here we had a b value that was this fraction. So when our b value falls in between 0 and 1, which this does, 1/3 is in between 0 and 1, we have a graph that's going to be decreasing. We call that exponential decay. Just some vocabulary. We'll talk more about that in the future. All right, let's go ahead and do another example. Here we have 13 times 5 to the x. So again, at our 0 value here, we're going to have 13. Our multiplier is 5. That's going to be a growth graph, right? It's going to be increasing because that b value is greater than 1. And I'm going to use the starting value multiplier approach to help me fill out this table. So 13 times 5 is 65. Let me double check that. I'm pretty sure that's the case, but okay. And then we will multiply it again. So 65 times 5 is 325. Kind of getting big there. And then to go backwards in our table, of course, we need to do the opposite of multiplying. We're going to be dividing by 5. So 13 divided by 5, that's 2.6. And then 2.6 divided by 5 is 0.52. 0.52. We've got a lot of decimals here, and that's okay. We're not really worried about the exact values. We can go ahead and round those, or we can estimate those when we go ahead and graph them. Now, just a quick confirmation that these were the right values. 13 times 5 to the negative 2. You can see here when I plug in negative 2, I do get that value of 0.52. When I plug in negative 1, 2.6. When I plug in 2, I got 325, right? So I got the right values there. Hopefully that was enough to convince you. Now I need to scale my axis. These are a lot of kind of strange numbers, 13, 65, and so forth. So I'm going to just count by tens. So 10, 20, 30, 40, 50, 60, 70. Okay, so counted by tens, 10, 20, 30, 40, 50, 60, and I'm just going to have to approximate some of these numbers. So I'll start with this one, 0, 13. That would be just above 10 here, right? Not quite to the middle there where 15 would be. 165, so it'd be all the way up here in between 60 and 70. And then negative 1, 2.6. That's going to be, 5 would be here between 0 and 10, so closer to 0 than that. So I've got my 3 points. Again, we want to make sure to include at least 3 points. And then 0.52, we could even approximate that. That would be very, very low, almost on the x-axis. So like I said, this is a growth graph. It's increasing, starts down low and goes up. And we'll try to sketch that curve in. There we go. It does keep going in both directions. Now, quick note, our scaling is not the same as the last graph, but it's similar enough. You can see how the second one here, this 13 times 5 to the x, is a little bit steeper, going up at a more vertical rate compared to this one. It's not quite as steep, and that's because of it having a smaller multiplier, right? It's not going to be going up as high as quickly as this one where our multiplier was 5. So it's kind of you can kind of compare their relative growth rates. This one being multiplied by 5 versus this one being multiplied by 3. And the larger growth rate results in a steeper looking graph. All right, last example. Here we have y equals 20 times 1/2 to the x. So again, starting here at 0, that's going to be 20. That's our a value. And we are multiplying by 1/2. Or, if we prefer, dividing by 2, right? Multiplying by 1/2, that's the same thing as dividing by that denominator, dividing by 2. So we get 10. 20 divided by 2 is 10. 10 divided by 2 is 5. And then to go backwards, right, we would do the opposite of that. We'd multiply by 2. So 20 times 2 is 40. 40 times 2 is 80. And again, just a quick confirmation here. I'll just show that it works for that top value there. So times 1/2 to the negative 2 power, right? So when I plug in negative 2, yep, I got 80. Hopefully that's convincing enough to know that it works for the rest of these here. So in this case, I'm going to count by tens here, but I'm going to split my graph up a little bit nicer. So 80 all the way at the top, 40 here in the middle. Those would each be 60 and 20, and then I'll mark lines in there for the tens. That can be another way that you do it, just to keep cutting your axis in half and scaling in that way. It can be nice too. All right, so I'll go ahead and plot these. I think I should be able to plot all these points. So -2 is all the way up at 80. -1 is at 40. 0, we are at 20. 1 is at 10. And 2 is at 5. So you can see this is a decreasing graph or exponential decay. And it's not very steep, right? Because our multiplier here is 1/2 dividing by 2. That's not a very big number to divide by, right? If it was like 1/10 or something like that, that would create a much steeper decrease, right? Because dividing by 10 makes a much bigger difference compared to dividing by 2. Same thing as multiplying by 10 is bigger than multiplying by 2. Anyway, here is our graph. All right. Good luck on the worksheet. See you guys later.